Okay, so welcome to Robotics, ME302. Today we're going to be talking about Denavit Hartenberg notation. This is basically another way of defining robotic actuator through the use of forward kinematics. So the actuator we're going to be looking at is actually going to be what's considered a wrist most of the time in robotics. You've got a joint here that comes up, and then it goes to a joint like this. And then that goes, both of these are rotational joints, or revolute joints, however your professor has defined those for you. And then you have a translational joint right here. And it's going to be going up. And there's the effector right here. Sorry I made this a little close to the top, but it'll be alright for the purposes of what we're doing. So the real secret to DH notation is how you define the axes. Usually what you can do is start out, you've got a base down here. You have to define the axis of each. Well, actually, before we even go to the axis, let's just name the joint. So this is going to be J1, joint 1, J2, and J3. Make sure you point them out to the side because it's going to get really crowded in here pretty soon when we start drawing everything everywhere. Okay. So DH notation has several rules, and actually exactly 7 rules of how to define each one of these joints as you're going through them. So it can get a little bit hairy, but just to get this cleaned up right off the bat in order to make DH notation work, when you're using DH, you do not consider the base or the end effector axis as they stand right there. You only consider what's happening in the joints. So that's something you can eliminate right off the bat, and you would calculate it later using traditional forward kinematic equations. But in order to get what DH can give you, you have to focus only on the joints. Now, first of all, we have 3 joints. 3 joints. So our DH table will have 3 rows. 3 rows. So if we're going through our DH table, B, zeta, zeta, A, and alpha, just like this, we're going to have from joint 1 to 2, but that's, well, actually, I'll talk about this. I'll just make the 3 rows right now. Sorry, there's so much you can do with DH that it's really confusing to pick a very clear way of doing it. I am not going to define the rules for you. I'm just going to go ahead and do this example and just crank right on through it. So what I like to do with this part right here is this is L not L1, L2, and then this is going to be Q, rotation of Q1, rotation of Q2, Q2. This is 2, a nomenclature, not squared. And then this is going to be a displacement of Q3. Alright. Make sure I got all those aligned correctly. Yes. So yes, the L1s depend on the axis, the joint which you're working with. So the L1 or the Q1 all are within relation to this. So I'm going to redraw this arm over here. And I'm going to put that first rotational actuator down by the base, and I'm actually going to extend this up like this. So just like that, and then the box. If you want to fast forward a little farther on to where I'm farther into this, that's fine. But I want to define this down here, and then this will become L0 plus L1. And the reason I want to do this is because when you're doing the displacement from an actuator from the base, you have to include this entire displacement in order to get the correct DH notation. And it would be the same for this actuator. If this actuator wasn't all the way over to the edge, you would, and it was out here in the middle, say like right here, you would have to combine these 2 lengths in order to get the correct translational direction. And we'll go over that here in just a second. But what we're going to do is we're going to define the first axis system here. This is going to be x0, x0, y0, and z0, just like that. And when defining these, you always have z in relation to the axis of rotation or displacement. So you'll see this in a second. And then y will always be in relation to the common normal and we'll talk about that in just a little bit. I'm going to go up here, I'm going to go ahead and define this axis up here too. This is going to be Z1, Y1, and then back where is X1. Now how did I get that? When you're defining the next axis, right here is a point that we're going to call O1 equal P1. O1 is the intersection of the common normal with ZI. And ZI is actually 1. This is going to be Z0 is Z minus, ZI of minus 1. So if you know the rules for Denavit already, you'll understand how I got this. Because since this axis and this axis intersect at a single point, this point is going to be O1. And then when you're defining Z, you do it with respect to the axis. But then to get X, you get X by taking the cross product of Z0 with Z1. So if you're using right-hand rule, you probably can't see it. But my thumb is put your fingers in line with Z0 and then curl towards Z1. The direction your thumb is pointing is X1, so into the page. And then Z1, of course, is the normal positive representation of Z1 from there. You'll notice that Z1 normally will point in the direction of the axis previous to this joint. So Z1's in line with this axis. And when we go ahead and run through all that again over here, you'll have Z1 in the Z2 in direction of the transverse direction. And then Y1 will be outwards like this, or Y2 will be out here like this. And then X2 will be positive out of the page. And as before, it's this right-hand rule with Z1 and then Z2 gives you X, and then you can get Y, and Y is normally there. And then this point is going to be 0, 2 equal to P2. 0, 2, and P2 are two separate points, but since they're at the same location in this case because of the intersection between the axes, they're the same point. So you can see the patterns here. With these axis systems, they are always one, the exponent or the name of it, Z2 or whatever it is always going to be one less than the joint number. So these are Z0 because this is joint 1. And that's how that continuation works. And you'll see how it goes in a little bit. So I'm actually going to add a little more to our DH table here. So the joint location basically out here on the edge. Because we have 3 rows, we're going to have the 0 axis to the first axis to the second axis, and then the second axis, second axis to the third axis, which will actually be the end effector in this case. So I'm going to go ahead and just add in a little bit of rotation here. You can do this, the sliding motion, and then perpendicular to that. Just so you know how the end effector works. But we're going to mainly focus on these. So within doing these, D is the distance from, make sure I define this correctly for you. Define that D is the coordinate of PI along ZI1. So from P1, PI, along the axis is Z minus 1. So it's basically this transverse direction right here. Because it's along the axis of Z1 and it's the coordinate of P1. So that's going to be right here basically. I mean, this can all be one point if you want to think about it like that. So that is going to be L0 plus L2. L0 plus, or L1. L0 plus L1. I apologize. Alright, and then theta, or theta, well, it is the rotation about the x1 minus xi minus 1 axis to x1 about the zi minus 1 axis. So how do you get this x0 to this x1 by rotating about this axis down here? Well, it's going to be 180. But you'll notice that since this is a revolute joint, we also have the q1 to deal with, this rotation. So x1 will always be 180 plus whatever q1 is. So 180 degrees plus q1, however many degrees this rotates as well. And then A is the distance between O and P, but in this case they're the same point, and that's going to equal 0. And if you don't know why these are the same point, go back and review how the rules are done in Hartenberg, DH. And then alpha is the angle from zi minus 1 to zi about x minus xi. So about this axis, find the angle from this z to this z. Well, if you look at it like that, and again using right-hand rule, you put your thumb in the direction of x1, curl your fingers from z0 to z1, and you'll find out that it's a positive rotation of about 90 degrees, because it's from here to there. So 90 degrees. Alrighty. Now, moving on from here, you'll notice that when we do these joint locations, we always go from this joint. We can include this joint in the application. Whereas in the previous forward kinematics that you may have learned, you usually do the second joint in the sequence. Like you go from here to here in the old style, but with DH you go from the bottom of this joint to the beginning of the next joint, and you only consider the very first joint in that sequence. So that's how to do this. So we are only consider the 0 axis, which is joint 1, for this whole row. And that's what this is useful for. Alright, so from going from 1 to 2, this axis to this axis, well, you have a displacement of L2. This is L2. You can see it up here, right there. L2. Alrighty, that's fine. And then you have a revolute joint again. So you're going to have a Q2 plus, well, if you're going from X, again, looking at these rules, you have from X1 to X2 about the Z1 axis. Right-hand rule, it's positive rotation of 180 degrees, so 180. And it's really important that you make sure you have these signs correct, because when you create your kinematic equations, these signs are going to be very, very important. Again, these 2 points are in the same location, so that's going to be 0. And then alpha is, again, the rotation from Z1 to Z2, or Z2, about the X2 axis. So right-hand rule, Z1, Z2, positive 90 degrees. 90 degrees. Alrighty. And now from 2 to the end effector, this is going to be Y3, Z3, and X3, which are the sliding direction, approaching direction, and normal direction of the end effector. That's how that's defined. You should know that already. But then what you do is going through here. The distance is actually going to be Q3 because you have a transverse joint here. So the distance is going to be whatever Q3 is. And with transverse directions, you always want to detail Q3 in the direction that's positive with respect to that axis. So like right here, we're moving positive in the entire axis system, so it's a positive Q3. You don't consider any kind of a length down here, or the fact that it can move this direction. Only the approaching direction will define what is positive and what is negative. Alrighty, and then zeta, well, you can see that this axis, x2, the axis 2 and the axis 3 align perfectly, so there's no rotation going on about any of the z-axes. The points are in the same location again because the normals intersect. So that's 0, and then alpha is also 0 because again no rotation. These axes align perfectly. And that is your DH table for this particular revolute transverse system. This is normally considered a wrist, and you can see how that is because you have a rotation about here, a rotation about here, and then kind of an approaching sliding rotation. So this is normally considered a wrist when you're looking at actuators. Okay, let's see here. Is there anything else that I can give you? Any of the other little tricks and things to watch for? No, I think that's it. Alright, so that's a quick example of DH Hartenberg notation. I'm just going to go ahead and carry this on. From the DH, you have the DH equation, which is equal to, give me a second here. Zeta I minus sine zeta cosine alpha I sine zeta I s alpha I A, I, C, beta, I, S, beta, I. Actually, I'm going to let you fill in the rest of this, and I'll just add a different video with all this stuff, but you should know this equation if you've been introduced to DH notation already. So, using this, you are able to find the homogeneous equations of A, say 0 to 1, A1 to 2, A2 to 3, dot, 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 using this matrix. From that, you're able to create the homogeneous equations and transformations and matrices in order to get a complete representation of this arm using matrices or the equations, whatever it is. But it's important to remember that we didn't include the base coordinate system or the final end effector coordinate system. Those would be a separate chunk of work that would be done using traditional kinematics. But in this case, this would also equal y base, z base, x base, so on and so forth. And then this one would also equal ze, so on and so forth. And then you would define the rotational and translational matrices about those. They would end up being identity matrices most of the time. And then from there, you can solve this entire actuator system. So that's the equation you need to use if you want to go any further than that, but this is your basic DH table.